All right, Chapter 8, Cryptographic Technologies. What we're going to talk about in this chapter from a very high-level perspective, just really all the general terms and the general technologies that we have to allow us to build things like IPsec, VPNs, clientless VPNs, client-based VPNs, site-to-site tunneling, and actually these cryptographic standards are also applied to many other functions like key exchange, the whole process of certificates and so on. One of the basic functions of cryptography is a cryptographic hash. As you guys are probably already aware, a hashing function is not actually encryption, although I guess technically it's encryption, but it's not really intended for the purpose of hiding data. It's intended for the purpose of verifying the integrity of the data. A hashing function by itself doesn't actually do that, right? If I'm going to send him data, I go and run that data through a hashing process and I send him the data. What is going to prevent anybody from in the middle intercepting that data, throwing away the hash, changing the data, recomputing a hash, and sending it on? Nothing. So a hashing function by itself doesn't necessarily provide message integrity, okay? It depends how the hashing function is applied. All hashing functions, but there's really only two primary ones, MD5 and SHA, but all hashing functions take an arbitrary amount of data, they run it through what we call a one-way mathematical function. The reason they call it a one-way mathematical function is because they're irreversible. Essentially, the math is so complex, it's easy to do forwards, but it's very difficult to do backwards. So when data gets hashed, you can't decipher that data from the hash output. But we take a variable length of data going into the funnel, and out pops a fixed length message digest, or what we call a message authentication code. Okay? What do they mean by the last two bullet points? Avalanche effect and collisions. When it comes to a hashing algorithm, these are two very, very important concepts. Avalanche effect. Anybody have any idea? You're on the right track, but let's think of it from a positive perspective. If I hash the big brown dog took a dump, right? If I do that over and over again, it's going to result in the same output. If I say the big brown dog took 2 dumps, very similar input, but the hash output should be completely different. So what they mean by the avalanche effect is if I change just a little bit of the input data, it should result in a completely different output. That's good, right? We don't want to have any kind of way of predicting what's happening in this process. I don't want to see some similarities between two different hashes so that I can start to interpret what the commonalities are between those two different functions. So that is a good component of a hashing process. Any kind of minor change on the input results in a major change on the output. Collisions, on the other hand, are bad. In a hashing function, a collision means that there is a possibility that two separate inputs result in the same hash output. Okay? Actually, believe it or not, that is a potential in some of the older algorithms, but you never want to have the possibility of two different inputs potentially resulting in the same output, because that completely negates the ability to verify the integrity of the data. All right? So whenever you talk about a hashing process, these are kind of the two things that always come up when you're talking about that. Hashing by itself doesn't really protect us. What scenarios do we usually use hashing just by itself? Files, right? Hashing files, something static, data at rest or whatever. You're downloading a file, it's going to have a hash tied to it. And that's typically where we have some sort of static hashing function. But if it's data in motion, and we're trying to protect the integrity of data in motion, we never just use a hashing function by itself. There's always some sort of secret sauce that gets thrown into the mix. And that's usually some sort of secret key that the sender and the receiver know. The reason why this is important is this is what it does two things. Well, actually kind of three things. Number one, non-repudiation of origin. Well, it actually doesn't do non-repudiation of origin. And the reason why is because everybody shares the same key. So you can't really tell where it came from, you know, in that sense. But it certainly does authentication. Not authentication to an individual peer, but authentication in that you're supposed to be sending me this data. What else does it do? It defeats man-in-the-middle attacks. How does it defeat a man-in-the-middle attack? Because the person in the middle doesn't know the secret key. Even though they might still be able to intercept the plain text data, they can't modify it and send it back out with a new hash because they don't know the key. Make sense? All right. Adds authentication to integrity insurance, meaning that you have a key, so you must be legit. Yeah, that's hashing with HMAC. So here's an example where authentication. Well, we just saw this in the previous chapter. I want to send a routing update, but I want you to know two things. I want you to know that that routing update came from a trusted source, me, and I want you to know the routing update hasn't been modified in transit. So we simply apply a hashing process where we take the key, the routing update, come up with our hash, send the hash along with the routing update, and then we go and verify it on the other side. All right? Essentially two different types of hashing algorithms, MD5, Method Digest 5, basically uses a variable linked input data and generates 128-bit message digest. Not recommended, kind of a legacy protocol. Well, I don't know if I should classify it as legacy because they do have those drag and drops in the test, right? They were basically classifying it as do not use, right? MD5? Avoid, yeah. Well, because it's only 128-bit output. Now, is MD5 insecure? No, not really. But if you have something better, use something better. SHA-1, 160-bit message digest. It is slower because it's more computationally expensive, but obviously it's a little bit stronger in that the key space is larger, or the ciphertext block is larger. And then SHA-2. SHA-2, of course, has all these variations, what we call a next generation protocol, where we can do 224 bits, 256 bits, 384 bits, and 512 bits. All right, became the standard in 2008 for the DoD, which is probably what you guys are using today, SHA-2. Encryption provides another level. Encryption in this case is hiding data in transit, providing confidentiality. Two types of encryption. You've got symmetric versus asymmetric. Almost all of your bulk encryption is going to be symmetric because bulk encryption algorithms are very, very efficient. What's the most common bulk encryption algorithm that we use today? AES, Advanced Encryption Standard, which is based on the Rindell algorithm. We'll talk about that a little bit later on. But basically, you have two options. You can do symmetric or asymmetric. This slide is really just kind of identifying what the purpose of encryption is. You've got some sort of what we call crypto variable, the key. You've got your plain text data, right? And you've got your algorithm. DES, triple DES, AES, whatever that might be. You take that, you mix it together, and you get your ciphertext. And then the only way to decrypt that data is to know whatever the corresponding key is to decrypt that information. All right? Does encryption provide some semblance of message integrity?
Yes, because if they can't see it, they can't modify it.
Right. yes, in a sense, for the raw data, the plain text data, but somebody could still modify the ciphertext. And we wouldn't necessarily know that the ciphertext was modified. We might decrypt that ciphertext, get some garbage, but it can still be modified. You're correct in that the original message could not be legitimately modified, but we could still modify the data in transit if we so choose. It just might not be decryptable, or it might not make any sense. Cryptanalysis is the process, and if you want to learn all about this, on our YouTube page, there's about a 2.5 to 3 hour video on cryptography that I recorded. We're not going to spend that much time on it, of course, but part of my CISSP class where we got into some really detailed stuff. And we broke down AES to the bit level, basically, and talked about quantum key cryptography and using photons instead of instead of physics instead of math to do key distribution, all kinds of crazy stuff. All right. Cryptanalysis is the art or the science of breaking a cryptographic process. All right. In almost every single variation that you see here, what is the goal ultimately in any kind of cryptanalysis attack? You want to see the data. Yes, that's true. That's the ends. That's what you're trying to get to. But ultimately what you're trying to do, figure out the key, crypto variable. We almost will always know how something was encrypted. Based on the size of the ciphertext block, or based on different components of the data itself, we can always kind of identify how data was encrypted. And by the way, there are only so many ways data can be encrypted anyway, so we can kind of guess as well. Our goal ultimately in most cryptanalysis attacks is to discover the key. So when you think about these different options, brute force, just trying a bunch of different keys. Trying a bunch of different passwords, trying different combinations of passwords. Ciphertext only attack, where you get the ciphertext. This is the most common type of attack, really, because ciphertext is usually what you get to see. And you're trying to break or discover the key by just looking at the ciphertext. Obviously, we can get into a lot of detail on all these variations. I'm not going to really do that. Known plain text attack. Wait a minute. If I know what the data is, why do I care what the data is? Because I'm trying to figure out the key. Maybe I got part of the message. Maybe I discovered part of the message. Even maybe I discovered part of the context of the message. I can infer a lot of things based on context. You know, it's a message going between company A and company B, and I know that they're working on this big project. So their context could be used as well. But known plain text doesn't mean I know all the plain text. It means I know some of the plain text. And usually just knowing the plain text is not enough. You'd want to probably also know some of the ciphertext. So chosen plain text and chosen ciphertext is you're looking at specific blocks of data that you're aware of. All right. What about a birthday attack? Without getting into the specifics, well, I'd almost refer you to go look at this birthday paradox online. But you know, if I told you guys, and I don't remember the specific numbers, I never do, and I look it up every time, and I always forget it. But here's the gist of it. If I said, okay, I'm going to put a number of people in the room, and what is the likelihood that two people will share the same birthday? Not the same birth year, but the same birthday. And you say, well, it would be 100% likely if you put 366 people in the room. Right? Makes sense, because counting leap year, there's only 366 possible days in the year. All right? But the reality is, because of the way the math works, is you only need like 25 or 30 people in the room to guarantee, and these numbers are not accurate, so don't quote me on these, but to guarantee like an 80 or 90% chance that two people share a common birthday. So the percentages go way down as you know, as the number of people go down. Obviously, the percentage goes down, but it's not as much as you would expect. it's called the birthday paradox. Essentially what we're saying in this particular type of case is we're saying, okay, we don't have to analyze everything. If we analyze 80% or 70% or we do some percentage of the data, we can decipher or discover secret information without having to analyze everything or without having to have 366 people in the room. That's not the best way to describe that, but I'm tired and it's been a long day and we need to move on, all right? Meet in the middle attack. The middle is what? The middle is what? The key. I mean, ultimately, that's what I'm trying to discover. I'm trying to discover the key. So I can take known plain text and I can take the resulting known ciphertext and I can start to attack from both sides to discover the key in the middle. All right? Common middle ground to both of those things is the key. So that's what a meet in the middle attack is. Again, we could go into a lot more detail on each of these, but it's not really that critical for this particular class. If you're going to take a CISSP, yeah, you need to know that stuff in detail. Encryption keys. Modern encryption uses public algorithms and secret keys. The key length is one of the most important factors to determining the strength of the protocol. That's called the crypto variable. And the length of the key is called the key space. The longer the key, generally the more secure the algorithm, or at least the more secure the data. Because there's a thing called work factor. Work factor goes into calculating how much time and effort is necessary to break a system based on these different variables. And as the key length goes up, the work factor goes up. There are two predominant classes of encryption keys, symmetric and asymmetric. Symmetric, I'm using the same key to encrypt as I am to decrypt. Asymmetric, I'm using a different key to encrypt versus decrypt. So we'll see in the next few slides what that looks like. Symmetric encryption, pretty basic. You've got an algorithm, AES, DES, triple DES, these are all symmetric algorithms. You've got some sort of key input, and you've got some plain text, and you run it through the algorithm, that's going to generate your ciphertext. So this is the crypto variable, this is the plain text, this is the algorithm, and the output is the ciphertext. One of the things that you may or may not be asked about, but if you're interested in cryptography, something to know, is the difference between something called a block cipher and a stream cipher. What is the difference between a block cipher and a stream cipher? Any ideas?
Block cipher uses other members to help do the encryption process, but they don't necessarily have the private key.
Nope.
No, I said that wrong.
No, I appreciate the answer. I'm glad that you step up. That's awesome. But no, that's not correct. Here's the analogy that I use. If I want to change the color of water, and I'm using a block cipher, I take my hose and a bucket, and I fill the bucket up with water, and I drop in my drops of color. I'm changing the whole bucket of water at a time. A stream cipher would be like, as the water comes out of the hose, I'm dropping the blue coloring into the water as it comes out of the hose. Right? In encryption algorithms, most of my symmetric processes are block ciphers. You have a 128-bit key. You have 128 bits of input data. You put both of those into the algorithm, do XOR operations, shift rows, shift bytes, shift rows, shift bytes, mixed columns, whatever. But whatever process you're trying to do, and then you come out with a 128-bit output block. That's a block cipher. You're performing actions against blocks of data. So when you hear about like AES 128 or AES 256, those are block cipher protocols. So AES operates on blocks of data at a time, whether it's 128 bits of data at a time, 256 bits of data at a time, and so on. Block ciphers tend to be a lot more efficient than stream ciphers. In a stream cipher, you're actually doing obfuscation and encryption on a bit-by-bit basis as the data is flowing. So you can imagine that's probably a little bit slower, a little bit less efficient. All right? But as far as the basic concept of a symmetric algorithm, we use one key to encrypt. We use the same key to decrypt. And those keys will be anywhere from 56 bits up to 512 bits. These are your most common block cipher algorithms. DES, 64-bit data blocks with a 64-bit key. But only 56 bits are actually used for the encryption, so actually DES is not really considered a 64-bit encryption algorithm. It's considered a 56-bit encryption algorithm. That was actually by design, because at the time DES was invented, they had a specific chip that was built for encryption that could only store a certain amount of data. And the size of the key was based on what that chip could process and store. All right? Triple DES, which most people call 3 times DES, is, I guess, essentially 3 times DES, going through the DES process 3 times in a row. Sometimes you can use 3 different keys in the process. Sometimes you use 2 keys. Obviously, if I'm only going to use 2 keys, it's less secure than if I'm using 3 keys. So you could potentially call this, if I do 64 times 3, I could call this a 192-bit encryption process. But if I do 56 times 3, it's usually defined as a 168-bit encryption process because, again, only 56 bits are used for the encryption process. AES, Advanced Encryption Standard. It's actually a really, really simple algorithm. You can actually sit down, take 128 bits of data in hexadecimal format, take the key in hexadecimal format, and you can actually calculate every round just with basic math. All right? I mean, that's ultimately the goal of any encryption algorithm, is just to take some sort of plain text data, some sort of crypto variable, and mix up the data and spew out some crypto ciphertext. In AES, there's 11 rounds of encryption. You've got the main round, which is a Boolean operation against the primary key and then the data. And then you've got 9 subsequent rounds of mixing data with round keys, and then you've got 1 final round. Then you spew out your ciphertext. If you go out to Google and you search on AES process, you'll actually see a little flash demonstration that kind of walks you through how AES does what it does. All right? Other algorithms: Seal, IDEA, Blowfish, Twofish, Serpent. Sounds like a Dr. Seuss novel, but these are all other symmetric algorithms. Asymmetric. In asymmetric, what is the goal? Encrypt data with 1 key and decrypt data with another key. All right? In what scenario? So let's say that we have the 2 key options we have are private and public. All right? Those are the 2 options I have, a private key and a public key. If my goal is confidentiality and I'm sending data to Jesse, Jesse has a private and public key, I have a private and public key. And my goal is to send data to Jesse that only Jesse can read. What key would I use to encrypt the data? His public key? My private key? Okay, anybody else have an answer? There's only 2 other options: his public key. Well, he said his public key. You encrypt it with the recipient's public key. Okay? Because the only way that that data can be decrypted is with the recipient's private key, which is never shared. Now, you said the sender's private key, right? That's for signing.
Yeah.
All right? So you have to kind of consider what the action is. If the action is to provide confidentiality, use the receiver's public key to encrypt the data so that only the receiver can decrypt that data with his own private key. If my goal is to digitally sign data or non-repudiation of origin, but I'm not concerned about confidentiality, I will encrypt the data with my private key, and then he will decrypt the data with his public key. It's kind of like a hash, but it's a asymmetric hash.
His public key or with your
My public key. Yeah, which I would have published to him prior to the process, right? PGP works this way, SMIME works this way, and so on. You can layer those two approaches to get both, right? You can go through the first process of encrypting the data with the private key, your private key, and then encrypting the data again with his public key. So now you're providing non-repudiation of origin, message integrity, and encryption. Make sense? All right. We'll actually have a couple of diagrams that describe that, but the bottom line is very computationally expensive. Asymmetric algorithms use something called, well, actually they use, there's not really a name for it. I mean, maybe there is, but I don't know what it is. They use factoring of large prime numbers. Very, very large prime numbers. Very, very, very large prime numbers. What is factoring?
Determining, I know what it is, but just
Right, yeah. So what are the factors of 10?
2, 5.
2, 5, 1, 10, right? That's pretty much it, right? 2, 5, 1, and 10. But when you multiply two prime numbers together, there's only one factor, those prime numbers, right? So what essentially the way that these asymmetric processes work is they work on extremely large prime numbers and calculating the factors of the product of multiple of large, very, very large prime numbers. And I mean 100 characters long, or 100 numbers long, 1,000 numbers long, really, really large numbers. All right, where there's only one factor, but you can't figure out what the heck it is. It takes too long. So it is computationally expensive. RSA, DSA, LGMAL, all examples of asymmetric processes. DSA is really the modern one that we use today. It is the one that kind of replaced RSA. All right? So if my goal is to hide this data, this would be the public key of the recipient. This would be the private key of the recipient. If my goal is to digitally sign this data, this would be the private key of the sender. This would be the public key of the sender. All right? So Alice has Bob's public key. Yay. All right? Alice wants to encrypt the message using Bob's public key. Bob decrypts the message using his private key. Confidentiality, what we just described. Obviously, Bob would have to give Alice his key beforehand. This is maybe how email exchanges, private email exchanges work. You're going to get a certificate from the recipient. You're going to use that certificate to encrypt the data, and then you're going to send it over, and then only Bob can decrypt that information. For authentication, it's the opposite. Alice encrypts the message with her private key, which only she knows. Bob verifies the signature using the public key from Alice. Alice's authenticity is verified. Bob could do the same thing in the other direction. Bob could encrypt something with his private key. Alice could then decrypt it with her public key, and then this becomes non-repudiation of origin. It also, by the way, provides for message integrity. Because if I'm sending the encryption string or variable with the data, because the data is typically being sent in plain text, then somebody would have to know Alice's private key in order to recreate that information. That would be verifiable.
So is the private key presented in a way where somebody can't intercept it?
The private key is never presented. Private keys are never shared.
But it's encrypted with the private key, right?
I'm encrypting data with the private key, but the public and the private keys are paired together. They're like, you know, they're married together. The public and the private key are the public. So let's say, for example, I want to get a key. The CA never sends me a private key. I actually generate my own key pair, and then I send my public key to get digitally signed by the CA. The CA is never responsible for generating the private key. That's all done internally on the host, so nobody ever knows your private key. But the public and the private key are married together in a way that performing a mathematical function with the private key can be undone with the public key, and vice versa. Okay? So that's essentially what a digital signature is. I hash data or I encrypt data using my private key, which nobody knows, which means that it must come from me because I'm the only one that knows what this is, knows what this key is. All right? So we can use this digital signature for data integrity. How can we use it for data integrity, by the way? Well, integrity means that the data hasn't been modified. Agreed? So how does encrypting data with my private key, or at least generating a hash with my private key, ensure data integrity, even if I'm sending the data in plain text?
If the data was changed, then the hash function wouldn't work.
Yeah, the hashing function would fail, and the only way that anybody could recreate a hash that could be verifiable by a public key is to generate it with the private key, which the person in the middle doesn't know. All right? Origin authentication, I'm the only one that knows the private key, so non-repudiation of origin, and so on. Yeah. So here's an example where we're applying a digital signature to a purchase order. I want to buy something from thinKtank. I send in a purchase order for $1,000 or $100,000 because we're not cheap. And I hash that with SHA, right? And I'm using my private key to hash that information. Actually, I generate the hash and then I encrypt the data with my private key. So this is my purchase order plus the hash that was generated from the encryption process. So I'm sending the purchase order in plain text. But obviously you guys get the idea. We just talked about this. I get the purchase order, I look at the hash, I use the public key of the sender to reverse that function, and then I run it through the hashing process for the message integrity. So I'm applying an additional layer of message integrity on top of authentication. All right. The last thing we'll talk about, which will be very quick, is public key infrastructure. You don't really need to know a whole lot about this for the test, so I'm not going to get into a lot of detail, but PKI is a framework that allows us to establish trusted relationships. We call it the web of trust, or you know, this party of trust where we have a third party that's kind of independent of everybody, verifying the authenticity of individuals. All right, that third party is called a certificate authority. That is the central authority. That is the third party that's trusted by everybody. It's kind of like you go to a party and, you know, you go to a party with Bob, and Bob says, hey, this is my buddy Ben, he's a great guy. You kind of already inherently, because you trust Bob, you inherently trust that Ben is a good guy, right? That's kind of the same concept here. It's a little bit more official, of course, but I trust the CA, you trust the CA, so inherently we're going to trust each other. Does that make sense? All right. That's done by certificates. It's a document that binds the entity to a signature by the CA. Okay? Here's how it basically works. I want to, let's see what they got here. I want to be able to identify myself to my clients. So I need to install a certificate on my device that verifies to my clients that I am who I say I am. So I generate my private and public key pairs on my device. I generate them locally. And I send my public certificate up to the CA using something like SCEP, Certificate Enrolment Protocol, or using some sort of CSR, Certificate Signing Request. I send that up to the CA. The CA, through different means, they call me, they email me, they basically go through a process where they verify that I am who I say I am. Once they're confident that I am who I say I am, they sign the certificate. How do they sign it, by the way? Yeah, exactly. The certificate has data on it, and that data is information about me. What the CA does is it takes that data and it hashes that data with their private key of the CA. And the only person that can do that is the CA, because these are the only ones that know the private key. All right? So when that certificate is presented to a client on the web, this is now a signed certificate. The client on the web has the public certificate of the CA, so they can verify the digital signature. And because they verified the digital signature, they now trust this server, that the data on this server is accurate. Okay? So Bob has a private key. Alice has a private key. Bob, instead of sharing private keying information, which they only know, Bob is going to send his public certificate over to Alice. That's going to be the public key of Bob. Alice is Alice is going to send her public certificate to Bob. And because both of them have the public certificate of the CA, they can go through the process of verifying the identity of each other, and that's it. Okay? All right. Now, there are obviously reasons why a particular certificate might get revoked. What would be some reasons why a certificate might get revoked?
You get out of the Marine Corps.
You got out of the Marine Corps. Yep, you're done. Your company went out of business. You got caught up in some big old crime, some espionage or whatever. Lots of reasons, right? Or it could have expired.
Or it could have been compromised by.
Could have been, your private key could have been compromised. Public keys don't really get compromised, but certainly, or the CA could have been compromised, right? So the digital signatures are no longer verifiable. Lots and lots of reasons. But the problem is, as long as the date is valid, then what happens? The certificate technically is still valid, but it could have been revoked. So how do I find out whether or not a certificate has been revoked?
You asked the CA to compare it against the CRL.
Well, there's two ways actually. CRL is one, or we can use OCSP. Both of them essentially do the same thing. They allow us to identify whether or not a certificate's been revoked. CRL's certificate revocation list they're not real time. So I actually have to send a message to the CA and say, hey, I'm trying to use this certificate, or occasionally I'll download a CRL over once a week or whatever, and I can compare the certificate against that list to see if it's been revoked. OCSP, the Online Certificate Status Protocol, which is the modern method, is real time. If a certificate gets revoked now, and I try to use that certificate now, I will know that it's been revoked at that moment, because all of those transactions are happening in real time, as opposed to downloading some sort of list that has all the blacklisted certificates. All right? So we have two options, OCSP or CRLs, the more modern approach, Online Certificate Status Protocol. This I've already kind of gone through, but I'll just hit it up one more time. We only have this slide and one more, and I promise I'll get you out of here. But I kind of drew this when we were doing the SSH discussion and how certificates get exchanged and what they're used for exchanging keying material. So let's say that I want to set up an SSL connection to the web server. The first thing that I'm going to do is make a TCP 443 connection request to the web server. The web server is going to send me its public certificate, digitally signed public certificate. So I've now authenticated the server, but I can now use that server certificate to do something that's very important, which is to share a secret key. So I use software to verify the identity using the CA's public certificate to verify the digital signature on the public certificate from the web server. And then I use my software internally to generate a shared secret key. I generate the secret key. The web server doesn't. I then use the certificate that I got from the web server to encrypt that secret key. I send it over to the server. The server then uses, well, that's not what it, the server uses its corresponding private key to decrypt that information. Now we both have a common shared secret key that we can use for bulk encryption.
Is it the browser that's coming up with what the key is going to be?
No, it's operating system. Yeah. It's a mathematical function that's performed on the operating system. Yes, it's being triggered by the application, but the operating system is what's performing the function. All right? The last thing we talk about is, well, I don't really spend too much time on this slide, but obviously the most important thing in any cryptographic process is to make sure you have key protection. You have to have a way of generating the key. You have to have a way of verifying the validity of the key. If you need to transport the key or store the key, you have to have a secure way of storing the key. You have to have a way of exchanging the key over public domains. So key management is a very, very important concept. Obviously, there are many, many techniques and many, many options that we have to implement these things. But the purpose of this slide is to kind of give you an idea of the life cycle of a key, right? Generate the key, verify its authenticity, store the key or exchange the key, one or the other, and then at some point revoke and destroy the key. Right? You guys have a very specific process to get your CAC. You have to fill out paperwork, they have to get some certificates, you have to go and verify and verify your identity. There's probably some sort of a set of rules that you have to agree to use it or whatever. Anyway, that's all part of key management. When I say key, we're not just talking about like asymmetric keys. We're talking about certificates and asymmetric processes. All right, so that was our basic cryptography chapter, very, very high level. Not a whole lot of cryptography questions on the test, surprisingly enough. There's a couple, but maybe one or two. But tomorrow we'll just get into some VPN stuff and some firewall stuff. So tomorrow's the last day. We'll see you guys here at 08, and we will continue on.